All right, hello. Whoa. Hi, guys. So today we have a special guest coming from a bunch of places. This is Spencer Kimball. He is an ex-Googler, and at Berkeley, he co-created GIMP and GTK. Currently, he's at Square, but he's working full-time on an open-source project called CockroachDB, and I'm sure he'll tell you a lot about that. Let's give him a hand.
So, okay, this thing's on. Great. Thanks, Michael. So, Cockroach. This presentation really wouldn't be complete without talking a little bit about why we chose this name. It's not a name that most people react favorably towards, but really what it is, it's a neuro-linguistic programming trick. It's pretty well known that people remember things much more with much more strength and resilience when they hear something or learn about something in the presence of a very strong negative or positive emotion. So, like ideally, we would have found an amazing name for a database that was evocative of all the properties of it, that was super positive, but couldn't think of one. So, Cockroach, though, does get the negative aspect down quite well, and people do not forget it. So, I think it's doing quite well. And the name is evocative of the system's capabilities. Cockroaches, the old joke is that after World War III, the only things that would be left would be the cockroaches. So that kind of resilience is certainly one of the properties of the system. Another really big one is that cockroaches, they tend to colonize your kitchen pretty aggressively, and we want the system to be somewhat autonomous and to move out and handle or accommodate the available storage space that's available. All right, so this is sort of a malformed insect. It doesn't have 6 legs, but there's 3 primary capabilities that matter that we think are important in a database circa 2014. So those are scalability, availability, and transactionality. And we're going to explore all 3 of these in a bit more detail. So I've been working on databases and infrastructure for applications that need to use databases for like 20 years. And so have most of the other people that have been working on this project so far. And especially in the last decade, I found that most applications that I've seen and worked on need 2 of these 3. Scalability being the one that is becoming most crucial these days. And it's usually one of the other 2. But also what you do find is as an application matures, they end up wanting all 3. And when you have good developers and active developers, and they want something, they end up building it. And apps that try to build one of these capabilities at the application level, above the database, tend to run into problems. So this is just a slide about the current state of play. And it's a bit simplistic, but I think it's important to sort of locate where Cockroach falls on the spectrum of what's available out there. So traditionally, we had SQL stuff. That's been around for 4 decades, kind of crazy. And these things typically aren't horizontally scalable. I mean, when I say SQL, I'm talking about Oracle's the big one in the open source world. There's MySQL and Postgres, and not typically horizontally scalable. Although things like Oracle do provide upgrade paths. There's usually not synchronous replication, say between data centers. People have added that sort of capability, but typically it's sort of has a replication lag, and that may be short, but nonetheless, you're not going to have a synchronous consistency. The next thing that sort of came out, and this was circa 2003, I guess, or 2004, with the big table paper, was this concept of NoSQL. And here they relaxed certain transactional constraints that were part of SQL in order to have a more facile path to scalability and also availability. They gave up transactions, and they made certain things like joins much more manual and much more painful. But there was a certain glee that I discovered in the whole community out there of giving up some of what SQL has. And I think there's some reasons for that, which we'll discuss later. But people really did embrace NoSQL, and it was a very interesting new mindset. And things that I would classify as NoSQL, of course, there's the seminal big table, and you also have Cassandra, which is a big one, React, Dynamo from Amazon. There's quite a few other ones. So then, we have what's been coming out in the last few years, and this is this concept of new SQL is what I've heard it called, but there's lots of different things. Spanner, again, Google has come up with really the seminal advance here. Spanner with a system called F1 that was built on top of it, kind of tries to get all of the pros and none of the cons. And they mostly succeed. It's quite interesting. So the goal here is to have your cake and eat it too. And that's what Cockroach is aiming at, with some differences from Spanner for sure, but hopefully with the right set of capabilities and ingredients to make it work for people. So the first leg here is scalability. And I list it first because I think it is probably the thing that most people are looking at, and it's why in the last decade people have embraced NoSQL the way they have. And the key observation here is that data is ascendant. There's like lots of different, I'd say, kinds of data scale challenges. There's the very obvious one, which I'm sure is true for Yelp. It's certainly true for some of the other companies I've been talking to, like Dropbox and Tumblr, which has a 500 MySQL node cluster. There's just, many companies these days are web scale, and they have like an operational set of data that is so large, you just simply cannot put it in a single machine. You can't really scale up anymore. Then there's something that's a little bit different, which is more like Square. You could actually scale up a single node to hold their entire operational set of data. But the thing is, it's very easy to collect data these days, and Square does that, and they do that and far in excess of what would fit on a single node. And that kind of data is becoming increasingly valuable. The machine learning advances that have happened in the last decade make it so that you can actually mine a lot of that information for valuable business intelligence. So I don't think that there are even small companies anymore that don't have data challenges, data scalability challenges. So vertically scaling a single node is expensive, and there are limits on it. Square is actually a company that's been very interested in Virident and Fusion.io, and I hear that you guys have some Fusion.io as well. The cost of those things don't necessarily scale linearly with the capacity. When you get into things like Oracle RAC, the graph looks very, very, much more exponential, I'd say, and comes to an abrupt cliff at some point. So the very common approach to solving data scale is sharding. I was first introduced to the concept of sharding at Google using MySQL on their AdWords product back in 2002. And they started with something like, when I got there, they had 12 shards. And then they moved to 20, and then they moved to 30, and then they moved the table off, and now we were able to go de-shard back down to 22 or something like that. And it was, downtime involved in those things. It was very complex. You had to be very careful to get it right. All the application code was aware of the sharding, which makes it, difficult to maintain. It makes it, I say, unnecessarily complex. And you end up with things like broadcast queries to all of your shards, because in some cases you might not know, you might not have all the information you need to locate where the data is, which particular shard ID. In Google's case, that was a situation where someone would try to log in with an email address, and with a user ID you could find the shard, but with the email address you couldn't. So on the login, had to do a broadcast query. We ended up solving that by creating Bloom filters that had the list of hashed email addresses on each shard, and so you might get some false positives, but you could only broadcast your query to 1 or 1 to 3 shards instead of all 30 or however many there were at the time. That's just an example of where these complexity starts to creep in, and once you add one of those things, it's really hard to get it out, and you find yourself tripping over it. They're also limiting. This is another problem that Google ran into. I'm sure you can shard your data onto multiple machines and multiple databases. And if, let's say, an AdWords customer was your average mom and pop shop, that's no problem. They'd easily fit onto a shard. But eBay came along, and eBay wouldn't fit onto a single shard. So they had they didn't quite go there, but there was talk of shards. So that was an example of where sharding actually does get limiting. You still are beholden to the size of a single one of your nodes in the shard. So ideally, what we'd have here is horizontal scaling. So you put money into the thing. In other words, you add some disks, and you get a proportional increase in your scalability, your capacity. Also, as I just mentioned, you can have arbitrarily large, this concept of entity groups. So that would be like a merchant. In Google AdWords case, eBay. So there's no limit on those. And really, in terms of addressing this complexity issue, you're looking for zero fuss. You want your apps not to have any knowledge of the sharding. It makes the code much simpler and much easier to modify and to reason about. And you don't get these resharding, to more shards or to fewer shard problems and all of that, that comes along with that. Typically does involve downtime. Or if it doesn't involve downtime, you're talking about a whole bunch of complexity to get around it. So availability. This one takes a bit more explanation. So probably most of you have heard of the CAP theorem. This is something that was proposed by Eric Brewer and subsequently proven. This all happened somewhat recently, and it's a very interesting result. What the CAP theorem says is that in the presence of partitions in a distributed system, a database, or whatever the distributed system is, can only be one of two things. It can be consistent, can choose consistency, or can choose to be available. Cockroach actually chooses to be consistent in the face of partitions. You never hear about a database which is CA, in other words, consistent and available, because there's no such thing as a distributed system in the real world that doesn't have partitions. So it's really in the presence of partitions, are you consistent or are you available? So that doesn't sound so great. Like, does that mean Cockroach isn't available? That would be a kind of unfortunate system to put into production. But the A in CAP is very confusing. It doesn't really mean what you think it means. Available in the term available in the context of the CAP theorem simply means that nodes on their own are able to make forward progress. They can independently accept writes. As long as they're non-failing, they're expected to. It's a very strange thing to call available. It doesn't mean nearly the same thing as high availability, which is what I think most people care about when they hear the word available. In fact, a CP database can be highly available. The cost is really something that is called consensus latency. In a consistent system, when you have multiple nodes, they have to agree on something being written. Cockroach uses a protocol called Raft, but most of these protocols are variants of something called Paxos. As an example, in an available or an AP system, you might have two databases in two different data centers. Each one can independently accept writes. If one database goes down, the other one accepts the writes. At some point later, the other database comes up. You may have an inconsistent read situation there, but what happens is the two have a way to merge their conflicts if they diverge. If you have two different data centers in this example, and each data center has 3 nines of availability, and you can write to either one, that gives you 6 nines of availability. With something like Cockroach, you'd have to have 3 data centers. You need a majority. If you just had 2, it would still work, but you have to always, both of the 2 would have to agree, so that would actually make your availability very, very poor. So with something like Cockroach, what you do is you have 3 databases, or data centers, and if each one of those 3 likewise has 3 nines of availability, having any 2 at on any write agree actually gives you quite a high availability number. It gives you 5 nines and a 7. So it's actually quite similar to just having 2 data centers that you can write to independently. But the lovely side benefit of this is that with Cockroach, there's never any disagreement. When you go and actually do a read, you always get the correct answer. You may have to talk to 2 of the 3, but you are guaranteed to always get the value that was written. With an AP system, that's not true. You can write something, and on the very next read, instantaneously or close to instantaneously thereafter, you may actually attempt to read and not actually read the data you just wrote. That's a huge problem. And that's really what Cockroach is aiming at. This line here in bold, second one, if the data center loses connectivity and power, your app should not notice. But then with an AP system, your app does notice. It has to notice. It has to realize that it can have stale reads. The goal, sorry for the NetOps guys, but they're the only ones that should have to deal with postmortems, because data centers do go out every year and go out for 10 minutes, or they can have something quite a bit worse, or it could even be 10 seconds. But having to deal with that, it's not the 10 seconds, it's not the cost of the data center going away usually. That can usually be dealt with. In my experience, it's the sure knowledge that that problem can occur, and then it's all the things that we do as engineers to try to address that. So having something that's consistent and available, and by available, again, I'm talking about highly available, is hard. Apps can do it. In fact, at Google, Bigtable, in order to give it these properties, people built something on top of it called Megastore. And what Megastore was great. I mean, like essentially, most new applications after it was created used it to the point where they had hundreds of separate applications at Google on top of Megastore. But it was very slow. And it is slow because doing it at the level above the database is necessarily inefficient. And also to get that correct is hard. It's a very error-prone process. So ideally, you'd want the database to solve this, solve it once, and solve it correctly. So the third leg here, and I think this is a crucial one, but it's one that I think most people are the least interested in. So it's transactionality, and this is something that everyone learned about in their database class back in university. It's like atomicity, consistency, isolation, and durability. So really, that can be summed up in this all-or-nothing semantics concept, which is, over the course of doing, an operation, a transaction, either all of the writes and changes that you've made, the mutations you've made to the database happen in one atomic fell swoop, or if something goes wrong, no matter what you've done previously as part of that transactional operation, all those things disappear and they're never seen by anything else concurrently. It's a pretty powerful property, and really what it enables is a simpler programming model. With transactions, the operations that you're implementing in your business logic are much easier to reason about. There are ways to not use transactions and to keep a consistent database, but they make the applications very complex. One solution that I've seen and actually employed myself when I didn't have a transactional data store underneath was to actually create operation queues. So if you want an operation to occur, you put it into a queue, it sort of gets logged in there, and then it gets something else processes the queue asynchronously and pulls an operation off and tries to run it. If it fails, then the operation will not have been marked as complete, so it will have to try again to clear that operation out. So it stays in the queue. And the only way to really make that work properly is to make sure that every single operation that you run is idempotent. So it has to run at least once, but it may run more than once, and that needs to be okay. That needs to end up with the exact same result. If you maintain idempotence, you can actually do something like that. But I'm telling you, it's very, very complex and very difficult. And as your operations become more sophisticated and do more, the idempotency it's easy to have it fail in subtle ways. So it is really much easier to reason about applications when you have a real transactional model. So I'd say that in the operation queue being just one example of where you can get around maybe not having it. There are a lot of other things that people try, lots of little tricks and things. Compare and swap is a very common way to do it. But just like the operation queue and with idempotency, compare and swap type operations, they work with a very simple case and they get very difficult as your operations become more complex. You really want the database to do this hard work. If something like we'll get to more of the architecture of Cockroach and what it provides, but transactions actually enable some fairly sophisticated features on the database itself that will eventually lead to SQL support. But without transactions, arbitrary support of SQL would be impossible. So we're looking for, with transactionality, data integrity. I'd say observation here is that without transactions, you end up with half-finished ops. And with half-finished ops, you have a data hot mess, is what I'd call it. It's like, it starts off small. If something doesn't quite finish, the operation doesn't quite finish, and what you end up, let's say the operation is maintaining, in the application levels, maintaining its own secondary index. That secondary index doesn't get updated, but the sort of primary piece of data does get written. And then you have an out-of-date secondary index, which means you might have a dangling reference. These things do start to creep up in the code or not in the code, in your actual data store without transactions. They happen bit by bit. But in my experience, where it really blows up and you get this hot mess is where it's not that the computer that's running the operation crashes. It's that your code has an error in it. And it becomes, it's not something that you see in your testing environment. you push it into production, and you start getting some real volume through it. Something changes, and all of a sudden you start getting exception triggering, and every single operation over like 100,000 goes is throwing an exception and creating like bits of stuff in the database, and then you back out the code, and then you have to go in there and write a program to go try to clean it up and restore integrity to your data. It's a huge problem, and like not having transactions, I think is something that many companies and probably engineers in this room have dealt with over the last 10 years with the advent of NoSQL, and probably have run into some of these things. I think transactionality was something that we gave up too easily, and I think it's something we need back again. As I mentioned before, I think that when NoSQL stuff came out, there was like this certain it was almost like an industry-wide sigh of relief that, oh, we don't have to deal with transactions because we can't deal with them because the most important thing now is scalability. So like, okay, we don't have to deal with transactions. This is great. I don't have to know what read committed means. I don't know what repeatable read means. I don't know whether it's serializable and Oracle's bullshit serializable or whether it's like real serializable. It was like, people were happy to have that off their hands. I think, part of that is that transactions had a lot of overhead at a cost. And the other part of it was that, as I mentioned, this isolation level, you always wanted to have like the isolation level that didn't have any write skew or these weird anomalies that can occur with like the lower levels of isolation. But you knew that it was more expensive, and you didn't really know which one to choose. I mean, I look at these things and I get confused. Even though I'm trying to write this database, I still sometimes look at an operation and I'm like, I'm not sure what SQL isolation level I should be using for this. It's a very complex thing. I think these two things matter, and Cockroach aims to make them matter less. We want to have fast transactions and really have one default, very high level of isolation. Another point worth mentioning, sort of the last one on here, is that Cockroach, you're talking about building something that's a huge cluster. And company-wide, say, at a place like Yelp, you may have multiple products using it, multiple databases. In some cases, as products evolve, you want to do operations that touch multiple products. Add an item to one particular database, and then on another database change some information about inventory would be an example that is germane to Square. Transactions across databases are trivial, so they're just as supported as transactions within a particular database. So Cockroach implements a layered architecture. There's a level of abstractions from most abstract to most concrete. It starts with SQL, which is currently not implemented. And I imagine SQL is going to be something that takes years to get all the way to like a full, ANSI SQL standard. But the immediate goal with SQL is to hit the 90th percentile use case, so that you can do queries and joins and things across the database. But if you really try to use like sub selects and things like that, that's not going to work until those features are added one by one to try to like get that last 10% done. But SQL is the highest level, but it's also one that I think is most aspirational. It's built on something called the Structured Data API. And I think this one is what we're targeting for our beta. And I think the Structured Data API is what will allow people to use Cockroach in a way that makes it work for their applications. And what it does is it provides all of the familiar RDBMS concepts. So you've got schemas, you've got tables, you have indexes, secondary indexes, you can have full text indexes, geospatial indexes, all of those different things are provided. And the database keeps secondary indexes in sync with particular modifications to a table. That structured data API, you can use it sort of the same way you'd use Juke, for example. It would be more of a programmatic interface. You wouldn't use a query language to access it. The joins would be a bit more manual, which has some advantages. One thing that we see a lot is these things like Hibernate and Juke, when they do provide a very easy way to do joins across tables, they often don't inform the programmer in any reasonable way that they're going to end up doing a full table scan. So you write your code in your test environment, and everything works great because it's super fast because you have no data in your test environment. And then that thing goes into production, and you end up with a 10-minute query because it decided on a query plan that actually had a table scan. With the structured data API, that's less of a problem because things are a bit more explicit. But it has certainly the functionality to create a surface area for applications to use that I think is friendly enough. So the structured data API, which is a bit higher level, it's more like the traditional RDBMS stuff. It's built on top of this distributed key value abstraction. So this is sort of the highest level external API that Cockroach provides. And what it gives you is a view onto a monolithic sorted key value map. And everything that the structured data API does, splits that, gives you different schemas. Within schemas has, different tables. Tables may have indexes. All these things may be interleaved. All of that stuff is mapping those concepts onto different regions of this distributed key value map. And it's a very simple abstraction, but it's very powerful. And what it does is, if you send a put to it or a get to it, it knows, which node out there in the system to go and fetch information from. And if that node's not available, another replica or to get a majority. It's the thing that basically deals with farming out things in a distributed fashion. And it talks to nodes. Nodes correspond to a physical machine, where there's typically, that would actually also correspond to one instance of the Cockroach binary. A physical machine may have multiple disk drives, and there's a one-to-one correspondence between an actual device and a store. So within a particular store, you have some number of ranges. And a range is the lowest unit of storage in the Cockroach system. A range is somewhere between, I'd say we're targeting 32 and 64 megabytes. These things get moved around between stores. A store may have millions of ranges in it. But a range, what it is it's a small chunk of this larger distributed key value range. That may be many terabytes or maybe even petabytes or exabytes. But a range is just going to be a small little bit. It's a contiguous piece of that larger one. Range is also the unit that we do the replication at. So you may have, let's say, a range from key AA, C, E, F, something like that, to AA, B, or AAF or whatever, something like that. Just a small little chunk of data in there. But that particular range is most likely going to be triplicated as part of a RAF consensus group. So there'll be 3 replicas for a single range, and those 3 replicas will all be located on different stores. So let me give you some nice little diagrams, which I'm afraid are going to be a bit of an eye chart from where everyone's sitting. So these are the layers of abstraction I was talking about. You've got SQL at the top, which talks to the structured data API, which talks to the distributed monolithic key value store. And then you actually get down into sort of more the physical architecture. And we have 5 nodes in this particular diagram. And each node has a number of stores. And the stores correspond to actual devices. This one says it's SSD. There's an in-memory one here. So each one of these 5 nodes in this particular diagram have 3 different stores. Now within each one of these stores, this is kind of like that previous diagram shrunk down at the top. And then we have 4 different stores across 4 different machines. There are, again, very difficult to read, but what you have here is a series of ranges that correspond to the entire distributed key value map. In this case, just for simplification, it goes from the number 0 all the way to the letter Z, and it's broken down into little chunks. And the color coding here shows that store 1, store 3, and store 4 all have different, all have replicas of the same range, which is range 0 to 9. So each one of those has a replica. The next range in the whole distributed key value map is A to C. A to C is stored on store 1, store 2, and store 4. So these color codings just sort of associate that. But this is kind of hoping to give a little bit more insight into the fact that ranges actually have replicas, and that's the level. And they kind of float around on these stores, which are basically the actual data stored on the device. Let's go back. So with this architecture, we actually implement distributed transactions. I mentioned before that we try to make these very fast. And one of the ways we do that is we don't have locks. There are effectively locks, but they don't have the overhead of a normal lock. Also, I mentioned that we are trying to simplify the isolation story. And what we have as a default isolation is serializable snapshot isolation. Snapshot isolation on its own is what Oracle used to claim was serializability. Serializable snapshot isolation is true serializability. And what serializability gives you is the illusion, even though that you have concurrent access to a database, it gives you the illusion that every transaction is being run serially with no overlapping concurrency. So that's a very powerful thing. Now there's a concept that goes beyond serializability that has come into the vernacular only quite recently, and it's called linearizability. And this is something that Spanner provides. It's a very powerful additional guarantee. And what it gives you is a global ordering. Serializability gives you the idea that each transaction is run serially, but things can change order. And that's okay with serializability. With linearizability, you have a global ordering. Spanner actually gives you like an absolute wall time that things happen at. We'll go into this in a bit more detail because it's a tricky concept, but it's somewhat important. So we also use Raft, as I mentioned, which is a variant of Paxos. And that's how we keep our replicas of a particular range up to date. We've had to make a variation on Raft, which we call multi-Raft. Raft on its own is a bit pedantic. If you just implemented it, you would have a lot of trouble because each Raft instance, and again, there's a Raft instance per set of range replicas, has to do heartbeats amongst its constituents. Since the store may have millions of ranges, then you would have per store millions of heartbeats happening every second. You would have nothing else except for heartbeats in your system. So multi-Raft is cognizant of that and shares heartbeats between any pairs of nodes and also does some other things. So last but not least on this particular slide for architecture is this idea of homogeneous deployment. I was just talking to some of these guys at lunch about it. I think it's certainly last on this, but not least. I think it's a super important one. Many of systems that are distributed, especially that try to do all the things that Cockroach is doing, have a lot of different actors in the system. Makes it hard to reason about, makes your system quite complex. Also, I'm not good at it. I'm really horrible at trying to debug and deploy heterogeneous architectures. So this appeals to me. And the way that we do it is there's one binary. Every Cockroach node is the same binary. Every Cockroach node can take on the same roles. There may be roles that a particular node is elected to for a particular range that it's serving, but any one of the nodes is capable of all the same things. And the way that they interact is with a peer-to-peer gossip network. What this means is that there's no, or very few, external dependencies. We don't have a zookeeper that we have to talk to or that you have to install. We don't have a distributed file system that you have to be run on top of. Everything is one single binary. So you push that out to your machines, and you give each binary as a command line argument the stores that, the physical devices that it needs to serve up. And then you also tell it, here's your entry to the gossip network, which is either a round-robin DNS entry or just a list of well-known hosts. And that's all you need. And the nodes then coordinate, and like little cockroaches go and let you put information on all the devices out there. Okay. So a little bit more about the distributed transaction model. We implement a variation of two-phase commit. There's really no such thing as a one-phase commit. Maybe there is, but I think it would be a pretty landmark computer science discovery. There are three-phase commits and maybe even more, but we have, I think, a very interesting and performant version of a two-phase commit. The way it works is that as a transaction is underway, the writes are done as sort of provisional intents. We call them intents. Every write in the system is actually an MVCC system. In other words, like every piece of data that's written has a timestamp associated with it. And there can be multiple timestamped values for a particular key. This is actually extremely important for doing things like map reduces. You want to be able to add a historical timestamp get a consistent cut through your database. So for example, if you're doing a MapReduce that actually touches everything in a very large database, that might take an hour or hours to run. You certainly don't want that to sort of lock your database, that you can get a consistent cut at the top so no other writes can be going in while that thing runs through. That would be pretty horrific and actually just not practical. So what Cockroach lets you do is read through the database at any historical timestamp within reason. You can configure things sort of on a key range basis for how long it keeps historical information or for how many copies of historical information that you want to keep. But the defaults are pretty high, so you'll be able to go probably a day before anything is cleaned up, which lets you do really long-running MapReduces and so forth. So the MVC is very important. It's also the sort of undergirding that allows snapshot isolation transactions, which is what we implement. So in the process of doing a transaction, you write your writes, but what happens is the new value you're writing, in other words, the latest value with the latest timestamp for a particular key, is marked as provisional. So those things, you sprinkle those things through as you're writing. And then what happens is that's really the first phase. And you can do this all in parallel for however many writes you have in your transaction if all those writes are available. On the second phase, the actual commit phase of the distributed transaction, you modify just a single key. And that single key is located in a special transaction table. So the transaction table holds a transaction value, which is keyed by transaction ID, which has things like the transaction status, whether the transaction has been, is ongoing, whether it's been aborted or whether it's been committed. It also has the timestamp of the transaction and a priority, which helps resolve conflicts. So what happens is, if there's no concurrency and no conflict in the system, you write your intents, and then you change the transaction record to be committed, and you're done. At that point, you can return to your client. Everything's good. What you then do, so that's just a single write. In a more traditional two-phase commit, what you have to do is a synchronous round to all of the nodes that you sprinkled your writes at. And that means that you basically have to wait for the slowest node to respond. With this, you have especially with a large transaction, you have a much better expectation of latency. These intents that are left there, they are resolved after the commit returns to the client that it's finished. And they're done sort of as a best effort. The reason that can happen is that, let's say that the intents are intended to be resolved, but the machine that's intended to resolve them crashes. So they're left now. So we've got these dangling intents that are sitting there, even though the transaction's committed. What happens is they're cleaned up as they're encountered. If a reader comes along and reads a value that was written during that transaction and discovers an intent, it's forced to go to the transaction table and look up what the disposition of the transaction was. If it sees the transaction was aborted, then it's able to just clean that up and remove it. If the transaction's been committed, then it changes it from being an intent to being a committed value and then reads it. So that's basically the transaction model. There's a lot more details. The design doc, I think, is something that we'll share around if people are interested. You can take a look at it. So I mentioned linearizability. So we'll talk a little bit about that. It's a bit of a subtle concept. I explained what serializable means. It's this idea that each transaction is able to run in isolation as though it's the only one on the database. Cockroach provides serializability for all cases. So that's an important property right there. And I'd say most people consider that sufficient. But where linearizability provides an advantage over serializability is it prevents a concept called temporal reverse. And it's pretty easy to give an example of where this could crop up. So if you've got a distributed system and you have two transactions, each of which hits a separate node in this distributed system, and the distributed system has clock skew, as all distributed systems do. What happens is that you can write to the first node and finish your transaction, and then as a consequence of finishing that transaction, start a new transaction, which hits your second node, and write there and finish that. Now, clearly, according to absolute time, the first transaction happened first, and the second transaction happened strictly after it. However, if the clock skew on the second node that was involved in that second transaction is sufficiently far in the past, you can suffer temporal reverse. So you know that there was some causality involved in those two different transactions. However, the second transaction, which you knew was the second, can have an earlier timestamp. This could be a problem, depending on how you use the timestamps on your data. Many applications, this wouldn't be a problem. I actually think it's not that big a problem. But what Cockroach does in order to solve it is it gives the client tools to deal with the issue. And really, the trade-off for the client is one of either performance or correctness. So if the client wants linearizability, it can achieve it. If it cares less about it, then it can avoid worrying about it and proceed as efficiently as possible. So there's really two different ways that this happens. The first is an observation that this temporal reverse problem is one that you probably only care about if you're talking about causal events. So one thing happens and a message is sent and then something else happens. In those cases, the ordering does matter. The ordering, if it gets flipped around, is something that could cause a problem. On the other hand, if you have two completely independent events that come in and hit the two different nodes that have clock skew, and it may be the case that if you had two atomic clocks and you measured it and logged it, and then you went later and you saw that the things were out of order, they're independent events. Does it really matter? I think that observation is really what motivates this particular pseudo solution to the problem. And what this is every time you do a transaction, you're passed back sort of an opaque bit of information. It's really like the timestamp that transaction was committed at. And the client is then free to pass that to subsequent transactions. And what that timestamp does is it forces an ordering. So on that, in the case we were talking about, where you start the first transaction, you finish it, and then you do the second transaction, the client would pass this information along to the second transaction. And that would give it sort of a low watermark for what the timestamp that the second transaction can be committed at. So it will strictly order them. And the client can, if it's just a client that's hitting directly at Cockroach, it's of course very simple. If it's a client that, say, passes a message back to, say, some JavaScript client, which then resupplies it, that will also work. And that's something that if you really care about this causal set of events, then you can have your client be very careful about passing this around. So the second way to overcome this is exactly what Google's Spanner does. They have a very, very sophisticated way of doing this, but Cockroach can do the same thing. The way that Spanner works, just to give you a little background, is they actually have a very accurate time signal. It still has clock skew, because it's impossible not to have clock skew. They have gotten their clock skew down to about 7 milliseconds. By contrast, if you use NTP to synchronize your clocks, you're talking about, and you're relatively close to the NTP servers, then you have about 150 milliseconds, something on that order. So it's at least an order of magnitude more. What Spanner does with that 7 milliseconds, in other words, that very, very tight bound on their time signal skew, is when they do a commit, they always wait that amount after doing the commit. So in the case that I was talking about where we experienced that temporal reverse with Cockroach, Spanner would do that first transaction. Before they return to the client that the transaction was committed, they'd wait 7 milliseconds. So now, when that next transaction goes, no matter where it hits in the system, every single one of those clocks is going to be ahead of where the clock that they started at was, no matter how slow that new clock they get to is, because they're all within 7 milliseconds, and it waited 7 milliseconds, so it guarantees that all clocks have gone beyond that. So Cockroach can do the same thing. If you measure your maximum clock skew to be 150 milliseconds, Cockroach can wait 150 milliseconds. And it will have the exact same linearizability properties as Spanner does. It's actually our contention that as these distributed, sort of geo-replicated databases become more popular, the infrastructure providers out there, like Amazon Web Services, for example, can provide more accurate clock signals. We expect them to. So, I actually expect this problem, this distinction between the two systems to fade, as a more accurate clock signal makes the waiting not such a problem anymore. And really for someone like AWS to do this, they have a real economy of scale. Buying a GPS receiver or even an atomic clock is not expensive. And it's really, it's about them implementing the, time signal distribution infrastructure within their data center. You've got to have the right servers that are passing that around so that every virtual machine has like an accurate signal. It's something they can do, and as demand increases for these things, it's something I believe they will do. So actually, this whole temporal reverse problem that I was just talking about, when I was reading the Spanner paper over and over and over again, trying to figure it out, I couldn't understand why that was such a big problem. Like, why would they go to all of the trouble that they did to solve this idea of temporal reverse? I think there's just a very small set of applications where that actually makes a difference. So I sort of stopped pounding my head against it and went and asked some of the people at Google that actually wrote Spanner. And they were somewhat amused that I thought that was really the problem they were trying to solve. They said that they told me what the real problem was, and it's about choosing a timestamp when you go to read. For a system to be consistent, a distributed system like this to actually claim it's consistent, one property sort of rises above all the others. And that is, if you do a write and you finish the write, and then you do a read afterwards, strictly afterwards, you must see the value. So that means that you have to choose a timestamp somehow that is guaranteed to be at or above the timestamp of any write that's already occurred in the system. So with Spanner, and they actually implement something called true time. With true time, this is very trivial. You just take whatever the current clock value is. And you know that anything that has already been committed has to have been more than 7 seconds behind you in absolute time. So whatever your signal is, even if you're slow, you're absolutely going to read something that's already been written. So for them, it's trivial. If you actually always do that commit wait, you can just choose your current clock time. But with Cockroach, we've had to do something a little bit more convoluted. This is all, of course, assuming that we don't get an accurate clock signal and we don't wait. So, as I described before, Cockroach doesn't wait on the writes. What we do instead is we sometimes wait on the reads. If we always waited on the writes, that'd be 150 milliseconds, which would suck, right? So the observation here is that most of the time when you go to read a value, there's no confusion about how recently it may have been written. The real problem occurs if you go to read a value, let's say at timestamp t equals 0 milliseconds. And you get to that node, and the key, the most recent value of the key you're trying to read is actually at time equals 5 milliseconds. In that case, you're not really sure what happened. If there's a significant clock skew there, it's possible that the t equals 0 that you think you're reading at was actually either, it could be one of two things. It could have actually happened before that write, or it could have happened after that write. You really don't know. There's this, say with NTP, there's a 150 millisecond window of uncertainty there. So, but as I said before, that situation, while it does occur, is somewhat unusual. Most of the things that you're reading are seconds old, or minutes or days, or maybe even months old. So what happens is that when you do trip across this small window of availability, you have to actually take some action, and that's where you incur the cost. And so we amortize it that way. The way that works when you start a transaction, I say a transaction because this is an important point. If you're just going out and poking at a single value, you just want to read a single value, you don't have this problem at all. Because with a single value, you just use whatever node you're reading from's clock as the current clock time. And that node, because it participated in the write of that value, it's guaranteed that its current time is going to be greater than anything that's been written to it. So with a single read, which is actually a very common case as well, it's not a problem. Now, on the other hand, when you're inside a transaction, so you have a timestamp that you're maintaining, then this becomes a problem. So what you do is when you start a transaction, you choose a time start, and that's just going to be the node you're on, current time. You also identify a time max. And what that is time start plus whatever your maximum clock skew is. So it would probably be time start plus 150 milliseconds. So what happens is as you go through the transaction you're reading, if you do run across a value that has a timestamp within this uncertainty window, then you have to restart. And the good thing, though, is that when you do restart the transaction, you reset time start to be the value of the values timestamp that you encounter that was in the uncertainty window so that you will include it. But you don't increase tmax. So what happens is you may have to restart multiple times in the case that you're of a long transaction and you read many values that fall within this window. But every time you restart the transaction, tstart moves towards tmax, but tmax doesn't move. So the total amount of time that you may end up retrying this transaction actually ends up being your maximum clock skew. So now, instead of always waiting for that on the write, you only sometimes wait that maximum on the read. So I probably should add another slide there, because I feel like that's a strange one to end the talk on. It's so in the weeds, but people always ask that question. So we'll send out this presentation along with the design doc to you guys, but this is an open source project. And we've actually gotten a lot of interest and a lot of people from around the world contributing to it, which is great. And I would encourage all of you to consider it if you have interest in distributed systems or want to learn more about them. We are Apache licensed. I think it's written in Go, something else I should mention. So if you have interest in Go, it's a great programming language for doing distributed system programming. And I would like to believe the code is very clean and well tested. And I think it would be a good system to contribute to. We also have an RSC channel, and there's a link here to the design doc. So that's Cockroach. Yeah.
Anyone have any questions?
My question goes to a little earlier when you were talking about all the interfaces, the abstractions that CockroachDB implements. You were saying, that you were having at the same time a key value stored with structured data. So actually, it means that, does it mean structured data as in SQL? You cannot change the number of columns, or what do you mean by it? And is that not kind of the opposite of what the usual key value store has, which is a variable?
Yeah.
Can you repeat that?
Sure. The question is, there seems to be, well, let me correct me if I got the question wrong. The question is, with the structured data API, are we losing some of the flexibility that you associate with NoSQL, where you don't have to specify a schema? Yeah. And the answer is yes. I think there's with the structured data API, there's more flexibility. We can do things. We could include column types, for example, that are sort of arbitrary maps of data. We can do interesting things. Spanner's done the exact same thing. They allow protocol buffers to essentially be the unit of storage. And so you can have like repeated fields and things like that within a protocol buffer. And you can get a lot of flexibility that way that is not available in traditional SQL. When we put a SQL interface on top of this thing, it will probably have some nods to that underlying flexibility, but it will necessarily enforce something of a schema. And the reason that you do need to specify your schema for something even like the structured data API is that you need to be able to update and maintain secondary indexes, and you have to identify what the types are of columns and how they're interrelated. And just adding one in the middle, involves some migration necessarily. You can use the key value store directly through an API, a very simple API. In which case you can do just whatever you want, arbitrary. In fact, the structured data API is just one choice that we've decided, and it's going to be, in many ways, a lot of compromises about what we think the right application interface is. But you can put anything you want there. You can make it look exactly NoSQL if you liked, but with transactions. You could do something that was strictly SQL. I think we're going to do something that's more of a hybrid.
Okay. So do you think that users interact in an SQL way rather than a key value store put and get way, right?
So the question is, do I think that users prefer to interact more with a SQL way or with a key value way?
The way that the pipeline seems to be that users interact with SQL.
Well, users can interact with any of these three layers. They're all available. Well, SQL is not available, nor is structured data APIs. Rarely was key value right now, but the structured data API will be what comes next, and then SQL will become after. But an application can move into any of those. And as I said, there's parallel ones at these levels. Right? You could put a NoSQL thing that's right next to the structured data API, and split that into half and put one half here, and they're both talk to the key value. And that could be both of those are external APIs that an application can program to. It's my contention that a straight key value store is insufficient for most applications. You always end up needing a secondary index on something. And you can build that yourself with the transactional nature that we provide with Cockroach. Our key value store is very powerful. You can say, I want to open up a transaction. I'm going to get this key and this key, and I'm going to put that key and that key. And it all happens at once, or nothing happens. And most key value stores, that's more of a dicey proposition, right? But in my experience, when you're actually writing applications, having indexes is just crucially important. And you can build them yourself, but it's kind of a pain.
One more question, and then we'll
Sure.
So you're trading off latency that is taken for writes and adding some more latency to reads in some way.
Well, you're hoping that the latency, the extra latency that you may incur on a read-only transaction, for example, over multiple keys, is not the common case.
Yeah. So that's why I was wondering, what are the sort of data sets that would be most well suited to CockroachDB?
So the question is, what data sets would be most well suited to CockroachDB? Give me an example of some data sets.
So I was thinking, could I, for example, store analytics data, like weblog data?
Well, typically when people store analytics data, there are more efficient ways to store it than the way that Cockroach is probably going to store it. For example, they use a columnar data layout. You can get a lot more efficiency. You can get like an order of magnitude more efficiency. That said, there's no reason that you can't store that kind of data in Cockroach. And in fact, I expect many people to. In fact, I actually think that there may be something of a false dichotomy out there between OLAP processing and OLTP processing. People use ETLs and split these things up into different systems, and then they have their analytics running on one offline, and then they. But if anyone's done that, there's it's a huge headache. There's first of all, you maintain two systems, all of the constituent moving parts. They also have these ETLs that you have to build that are moving things between them, which of course get fragile. And you're not really dealing with your up-to-date data. It would be ideal if you could do both kinds. And with something like Cockroach, where you're able to shove in commodity hardware and get scale out of it, it would be very advantageous if you can do both. And one of the things that's not discussed in this, but maybe something I should add, is a really interesting concept in Cockroach, which is what we call a minimum. It's a range-spanning binary tree. What it does is it provides like a way to, obviously a logarithmic number of steps, and parallel fan out like a large operation throughout like a massive key range. And this is how you'll be able to do map reduces. But map reduces will be like an absolutely integral part of this system. And so, I think that I would say Cockroach is going to be better for, say OLTP processing. That's really what it's geared at. But we are not going to be afraid to support a more wide range of use cases.
Thanks, Spencer.